add up all the values of the temperature in that solid. That's that function, right? The function takes the point and gives you a value. For each point in the solid, it gives you a temperature, 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 temperature. Add them all up, that's the triple integral.
So it evaluates the solid, some aspect of the solid?
Some aspect of a solid. That might be the, it could be the magnetic field, it could be a lot of different things. But this is a tool that allows us to add them all up, right? It could be the density at each point, right? The density. And if it's the density, then you add it all up, it'll give you the total mass. We're gonna do this with two-dimensional stuff. We're gonna get like a flat sheet that has variable density, and we're gonna find the center of mass. Actually, look at your take-home. It's one of the problems on there, actually. So there's application. The bigger idea here is the tool of the integral is to add things up. What you're adding up, you know, I don't want to go too far off on this, but it's such an important idea that I almost feel like I have to. Our traditional integral, Cal 2, right? What was your domain? What dimension did your domain live in? Your domain, the domain of this integral. Well, you're going from where to where? 0 to 2, right? That's what? Right? That's linear. So your domain, this is your domain here. It's from one point to another, right? And what are you doing? At each point in here, right, you have the height of the function. And you're adding all those up and you're getting an area, aren't you? But it's just the sum of all the heights. In a double integral, what you're doing is you're taking a two-dimensional domain, right? And at each point here, you have a height and a height and a height. And so when you add up all those heights, you get a volume, right? In a triple integral, your domain is now three-dimensional, right? And you're just taking the sum of all of, now you don't have heights anymore. It's just, you're taking the sum of all the values of this function at those points within the solid. But you don't have like a thing, where are you going to put height here? There's no more dimensions, you're out of dimensions, right? And then theoretically, now you're taking all the points in the four-dimensional solid, if you want to call it that, and you're adding all those up and you're getting something in a more and more dimension up. And this extends out to actually n dimensions, or you can actually have infinite dimensions as well. So, I mean, it extends, right? So this is like a fundamental, like big principle of the integral is this relationship. Okay, let's go. Next example. These are good questions. Oh, by the way, I should point out, yeah, no, this is the solutions from, I have the solutions manual. I don't know why I put that in there. Okay, there we go. How about this one? So I would love to give you 20 minutes to work on this right now and see if you can figure out, but that's not what, I mean, we just don't have time in this class for something like that. That's why you have homework. But I'm going to work through it, all right? So I need to find the volume of the solid that's bounded by the cylinder, y squared plus z squared equals 4. The planes x equals 2y, x equals 0, z equals 0 in the first octant. Okay. X is coming at you, right? Y is this way. All right. Y squared plus z squared equals 4 is a circle in two-dimensional space, but we're in three-dimensional space, so it's a cylinder, right? And it goes out which axis? The x-axis. So I have this cylinder coming out at you like this, right? It has a radius of 2. Y'all see it? Boom, coming out. Okay, now we have, let's do the easy ones. X equals 0. The YZ plane, right? YZ plane, cylinder. Z equals 0, the ground, right? The XY plane. So we've got a plane down here, this ground, this wall, and a cylinder going through. And then finally, x equals 2y. I don't like that. I'm going to do it instead of that. I'm going to do y equals 1/2 x. Same thing, right? And that would be in this direction here, you'd have over, right? Rise is this way, rise, and then runs that way. So you go over 1, out 2, and you'd have a plane like this. Cylinder, the ground, this back wall, right? And this plane in the first octant. So let's do what we did last time. Let's see if we can draw the ground first, right? Let's start to draw the, what's in the domain. So in the domain, I had x equals 0. I had, well, z equals 0 is the actual ground, isn't it? And then y equals 1/2 x. Y equals 1/2 x. Plug in 2. So if I go 2 this way, I only go up 1. So go like that. Yeah? I don't see a D, right? Do y'all see anything closed off? So what's going to close off any region? I mean, we definitely have to have something close off here. The cylinder itself, right? Because remember, that cylinder is going to come around and wrap, and then it's going to hit the XY plane, isn't it? It's going to hit here, and it's going to hit up here. But when it hits the XY plane, it creates 2 lines, doesn't it? 2 lines like this. And where do they hit at? At the radius, which is 2 here and -2 on the other side. So I actually have 2 more lines. I have one here, like this. And then I have one back here at -2. But I'm going to make that one dotted because it's not relevant, because I tell you to be in the first octant here, right? So at the very end, right, I say in the first octant. So we have, pardon? What did I do? Oh, yeah, I did it the wrong way. I'm sorry. That's my fault. My fault. It's the y, right? I put it on the x. My fault. And the radius is 2, right? So it would go this way, right? Oh, wait, hold on. Yeah, it goes down the x-axis. Yeah. So let's just put this one. I don't need the one below, right? Is that okay? I'm not putting the one down here, because if I'm in the first octant, right, then I'm basically up here in this region right here. Do y'all see the cylinder above this? Reps. It's not a very good picture, but the cylinder is like this, right? And it wraps like that.
That should be the line y equals 2.
Yes, this is y equals 2. All right, let's try and put some restrictions here, right? Let's get our controls. Let's describe this region right here. Let's describe it. So what is our x bounded between? Is this type 1 or 2? You could do either. Which one do you want to do? Type 1? Okay, type 1, the x is between what 2 values? 0 and 4, right? Because you'd have to go out to 4 here in order to come up here and hit right there at 2. How do I know that? Because this is 1/2 x, right, the red? So you have to go to 4 to go up to hit 2. Why is it 2? Because the radius of the cylinder is 2. So I go 0 to 4. The restrictions on y are between these two, right? We're stuck between these two, which is 1/2 x up to y equals 2. Right? Any questions there? So now all we need is just what's the top surface and what's the bottom surface, right? So the top of this surface is the cylinder itself, right? which means you have to take the cylinder equation and do what with it? Solve for z. Which means you have a square root, right? Which means you have a plus or minus. And we will take the plus because we are up in the first octants. So we would never have a negative z value, right? So solving that for z, z will be equal to the square root of just 4 minus y squared. And then what's the bottom? Just 0, z equals 0, right? So this right here is our f of xy, right? And then our g of xy is just 0. Now, I'm calling it f of xy because, you know, it is a function of two variables, just x doesn't appear here, right? Are we ready to set it up? I think we can actually set the integral up now. We're going to go 0 to 4, 1/2 x to 2, and then the top of the surface, or top of the solid, however you want to say that, minus the bottom, right? Do y'all want me to put minus 0 or no? No, don't need it. D what? D what? dy dx. That's it. That's the setup right there. Now, when you look at that integrand, could you integrate this? There's probably a formula for it, but in Cal 2, this is trig sub, right? This is trig sub. You got the square root of a squared minus x squared, but really we're using y. So you do trig sub. The sub would be replace y with 2 sine theta, and then you do trig sub. So that's doable, isn't it? Let's see if we would have done type 2, what would have happened. What if we change our minds and we say, let's go type 2 instead? So if we do type 2, now our y is stuck between two constants, right? 0 to 2. And our x's are bounded between two functions of y, which would go this way now, right? So the smallest value of y I'm going to get is 0, and the biggest is what I get when I take this and solve for x. So wouldn't that be from 0 to what? 2y? 0 to 2y. The advantage of that, as we're about to see, let's look at the new integral.
And the z is the same. It's
Yeah, still 0. Yeah, still 0. The ground up to the cylinder, exactly. But I'm gonna erase this, and we're gonna look at the difference on the integrals, and we're gonna see if we prefer one over the other one. So this one would go from 0 to 2, and then it would go from 0 to 2y, and then it would be still the square root of 4 minus y squared, but now we're going dx dy instead of dy dx. And we'll have that same thing happen that happened on that previous one, where we're going to integrate this with respect to x first, which would give us, you know, this times x. And then we'll plug in our two values. And when we plug in our two values, we're going to get a y in there with it. It's going to be a u sub in that new integral, just like it was before. That's a way better integral to do. Yes?
Why is it still
These are switched? You're good then?
looking at the wrong one?
Okay, yeah, this is the first, this is type 1. This is the one we did type 1, right? And this is the one that we did type 2. Got it? So the solution to this, which I'll let you, oh, do y'all want to see it? There's the cylinder, there's a plane and another plane and then another plane. And then the solid we are looking for is right there in that little space. We pull everything out of here, we can see the solid right there. We're finding the volume of that. And this is the actual work. The book, the author of the book, right, or whoever did the solutions, they chose to do this using the type 2. And you can see they did the antiderivative of this, which just basically put an x to it. Then they plugged in 2y and 0. There's your 2y. The 0 kills it off. And then they did a basic U sub. They don't show any of that work. There's your antiderivative. Plug in your 2 limits of integration. 16/3 is the answer. All right, that concludes 12.2. All right? Double integrals over rectangles, type 1 and type 2 regions, right? Moving on, 12.3. Double integrals in polar coordinates. Quick show of hands. How many of you have some experience, feel somewhat comfortable with polar coordinates? It's okay if you haven't. How many of you like really not just feel kind of like, I'm not sure about polar coordinates? Not sure? No? Okay. All right. Just trying to get a feel. All right. This is what we've done so far, right? We can do a double integral over those 3 types of regions. Rectangle, type 1, type 2. I don't need to cover that again, right? Now we are going to look at some regions that those won't work for, right? Regions that we actually see pretty frequently that you cannot classify as a rectangle, type 1, or type 2. And so we need perhaps a different coordinate system to deal with these other regions. So now we talk about polar coordinates. And if this is your first time seeing it, it's okay. In Cal 2 normally is where you see it, and I know in my Cal 2 we don't get too deep into it. And the idea is that by the time you get here, you can absorb it pretty quickly. It's not a super complicated idea. So the idea is this. Our traditional coordinate system is called the Cartesian coordinate system. Cartesian coordinate system means you have 2 perpendicular axes, right? Your x and your y axes. And if I give you a set of numbers, an ordered pair, right? X and y, if I give you that those are directions on how to get to some place in the plane, right? So I'll give you an x and a y. The x is going to be your horizontal displacement, either to the right or to the left. And then your y is your vertical displacement, right? Either positive or negative. So in order to get you to a point, that point right there, I have to provide you 2 directions, two pieces of information. The x and then the y, right? But there's another way I can tell you to get from the origin to that point. That doesn't require me telling you an x and a y. I could tell you, like, I like to imagine I'm standing. Here we go. Imagine you're standing. This is you standing right here at the origin, and you're looking out the x-axis. And I want to get to a point on the xy plane, all right? So I could give you the x and then the y, right? And then you're there. But I could also give you an angle to turn to, right? Point in a certain direction, and then I can tell you how far to walk out, and you will still get to that same point, right? So that is what polar coordinates is. It's just a different set of instructions on how to get from the origin to a point. It's not Cartesians. It's not the Cartesian coordinate system. It is the polar coordinate system. So I have to provide you an angle to turn through, and I have to provide you a distance to walk out. So the angle is theta, and the distance we walk out is r. And if we label this theta and we label this side r, then we have a nice right triangle from pre-cal, and there are relationships here, right? All sorts of relationships. The big relationship is that if I ask you what cosine of theta is, cosine is adjacent over hypotenuse, it's x over r, and then if you multiply both sides by r, you get an equation for x. X is always r times cosine of the angle. So there's a relationship. See, what this creates is a relationship between the Cartesian coordinate system and the polar coordinate system. The polar coordinate system requires 2 pieces of information, right? To get to a point, you need the angle and the radius, or the distance to walk, right? Still 2 things. Cartesian, you need 2 things, right? X and y. That you can never make it just one thing. If you need 2 things in Cartesian, you're going to need 2 things in polar, right? And then similarly, we can figure out what the y is by doing sine of theta, and that's y over r, and then multiplying both sides by r. And so So essentially you have this relationship that the x-coordinate is always that, and the y-coordinate is always that. Other relationships we have, Pythagorean, x squared plus y squared is r squared, right? That's a relationship between these sides. And then the final relationship has to do with the angle itself. Tangent of theta is y over x, right? Tangent is y over x. So let me show you the main polar coordinate takeaways. They're right here. This is everything I just said. X squared plus y squared is r squared. X is always r cosine theta. Y is always r sine theta. And then theta is the inverse tangent of y over x. Those are the main equations that connect polar and Cartesian together. Would you all like me to go in any more depth with that? Y'all are okay with that? Just the basic idea? Yes? Because we're about to go do double integrals in polar now. So, yes? All right. So, if I tell you this, right? Let's say I tell you that I want us to do a double integral in the domain on the ground. If I tell you that domain is the set of all x and y's such that x is between a and b and y is between c and d, what does that look like? If I write that down, what does that look like to us right now?
Rectangle.
A rectangle, right? That's a rectangle because xy, when I write xy down, I'm implying that we're talking about Cartesian coordinates here. So all of your x values are between two constants, a and b. All your y values are between two constants, c and d. So you create this rectangle, and that's it right there, right? All the points that live in this rectangle. Yeah? But what if I do this instead? What if I write this? D is the set of all points r theta such that theta is between two constants and your radius is between two constants. Now, I'm not going to use A, B, and C, D. Okay, there's a standard that we use for polar. Theta, alpha, beta for the, I want to match the book because different books use different things. Alpha and beta, so instead of A and B, right? And then for R, they use AB, which is just the way the book does it, okay?
Kind of like a pie slide, jump this up front.
Yeah, something like, so this is telling you that your angle, you're standing there at the origin, right? You're looking out the x-axis. Your angle is between two different angles. So let's say this is alpha. Let's say that's me pointing out the x-axis. So I'm between, let's say that's alpha, and then let's say beta. So I can only swing between here and here, right? And then my radius is how far I walk out, is stuck between two constants, right? So it's going to be like, almost like a washer. It's almost like a washer, but I'm only allowed to be stuck between two different angles, right? So it would just be something like that, right? My angle is stuck between alpha and beta, and my radius is stuck between walking out A to walking out B, between these two. Now, I have a way better little animation here for you. So look at me. I'm going to change A and B, make A smaller, make A bigger, make B bigger, make B smaller, and then I can change alpha, right? And I can change beta. Look at that region right there. Is that a rectangle?
No.
It's a polar rectangle. That's what we call a polar rectangle. It's not a Cartesian rectangle, but it's a polar rectangle because in polar coordinates, that is, your two variables are both trapped between constants. Yes?
You can still multiply by two sides.
You can still Oh, no, no, no. It's not. So a Cartesian what's the area of a Cartesian rectangle? Well, length times width. What's the area of a polar rectangle? Well, not length times width, right? So whenever we talk about things like geometric shapes, we have to actually know what coordinate system you're using, right? We always assume Cartesian, right? We always assume Cartesian. Whenever someone gives you a point, you don't say, oh, did you mean polar, right? I mean, it's just like the standard is Cartesian. That's what most people see. Like anyone who takes anything below calculus will never know of polar coordinates, will never know of spherical coordinates, cylindrical, right? Was there another question? Yeah.
What's the difference between this and just using the washer method to integrate?
Well, okay, so the difference is that in Cal 2, what we're doing is we're taking an area and we're wrapping it around an axis, right? That is very different than taking a region and just plugging those points up into a function and finding that volume. See, there's no rotations involved here. So even though that kind of looks like a washer, they're completely separate ideas. Yes?
For writing polar coordinates, you have known areas, it's r comma theta.
It's r comma theta, and I didn't state that. It's in the notes though. Because I'm kind of like breezing through this here. If you scroll back up, it says somewhere in here, somewhere in here, somewhere in here. Well, I don't think I explicitly say it. It's implied right there.
Yeah, I was.
It's always r theta, it's not theta r. Okay? It's always r then theta. Just like you can't flip x and y, it would change things, right? The r is always. So let me just, if I ask you to plot this point, and I put 3 pi over 2, right? I'm going back to a more basic problem. What this would mean is, well, in polar coordinates, this would mean that I rotate by pi over 2, right? And I walk up 3. 1, 2, 3. So I'd be right there. That's what it is in polar, right? If I didn't tell you that was polar, and I told you that was Cartesian, then you would go to the right 3. You would go up pi over 2, wherever that is, right? Those are totally different things. So I have to be explicit when I'm giving you this and tell you that that's polar. You cannot assume that because that's an angle that it must be polar, because pi over 2 is just a number, right? All right. We good? So now we know what rectangular polar regions look like, right? That's what a rectangular polar region looks like. So when you look at this polar rectangle right here, in Cartesian, it's not a rectangle. In Cartesian, it's not type 1. In Cartesian, it's not type 2. Do you see that this is an example of a region that you cannot do in Cartesian? Like what we learned in the previous section, maybe there's a way you could like break it up, but it'd be a pain, wouldn't it? To try and break this up to make it, like maybe you separate it and make a bunch of type 1s or a bunch of type 2s or a couple of type 1s and a couple of type 2s. But that's why we're doing this. This is why the coordinate system is so important, is because we're going to see this is very easy to do. Okay, let me remind you that when we were doing our double integrals, when we first introduced them, we had this domain on the ground, right? And what we said is we're going to cut these into small little rectangles, and then we're going to create these like boxes, right? All these boxes above, and we use the double integral to add up all the boxes. And we said that infinitesimal little patch on the ground there, that little infinitesimal patch, we called it dA. It was that little infinitesimal area. And it was simple to figure out what the dimensions of it were, because dx, that was our left and right, and our dy was up and down. And so dx times dy gave us dA, right? But that's Cartesian. Everything is orthogonal. Those axes are orthogonal. If you're talking about polar, nothing is orthogonal anymore. So when we convert over to polar, Imagine taking a polar region and zooming in on this little infinitesimal patch. It's not a rectangle anymore. It's something that looks like that, right? So this was dx, this was dy, right? And so that the area of that was dA. Just that times that. If we nudge x a little bit, right? This is a little nudge in x back and forth, a little nudge in y, right? That's the shape we get, a rectangle. But in polar, if I nudge theta a little bit back and forth, and I nudge the radius back and forth, I get that. Yeah? Question is, what's the area of that? Well, it's a little complicated. This right here is dr, okay? That's your change in radius, dr, right? It's just the length. It's how far you walk out. This is not as easy because we need the length of this, right? We want the length of that. We don't want the actual difference in the angle, right? The angle changes and that changes that length. So we have to go back to a formula from pre-cal. S equals r theta. I think I have this written there. So no, I think it's below. S equals r theta. If you take a radius r, start here and you swing a segment, a line segment through some angle theta, you will create an arc, and that arc will have a length of s. And the relationship here is that s will always be equal to r times theta. Do y'all recognize that formula?
Yeah.
Yeah? There was one condition here on theta. Theta has to be in radians for that formula to work. What if theta is 2 pi? What if theta is 2 pi? What is it going to do? Swing it and go all the way around, and you get a circle, wouldn't you? So what would the distance all the way around that circle be? R times 2 pi, 2 pi r. That's the circumference formula, right? So this is our generic formula in pre-cal that gives us basically the length of any arc on a circle. So what you have to see here is that this right here is like the S, and the distance from here to here is the R, and then this right here is d theta. D theta is how much the angle changes by. So according to that formula, this length will be this times this. Now, I'm trying to convince you right now that that dA that you see in red is this formula. Do you believe it is? I mean, what's S? We just said it was what? R d theta, or here R d theta, and then this is what? dr, right? Those three things multiplied. Would you agree? I think you should probably be having a problem with the fact that that's not a rectangle, right? Like, I'm acting like this is a rectangle, aren't I? Aren't I acting like that's a rectangle?